Okay, more on logarithm functions in lesson 6-4. So first we're asked to graph, well, what does the graph of log base 2 look like? And so if we're first looking at log base 2 here, log base 2, well, we also might remember that log base 2 would be the inverse function of 2 to the x. So 2 to the x, we graphed that earlier, and it looks like this. If you recall us, this is going to be the inverse. So 2 to the x right here, that's already the graph I have. When x is 0, y is 1. If you go out there to say x of 3, you're going to get an 8. If you do a negative number in here, like out here, you're getting really close to 0. So if we went really big, you're getting really close to 0. But on the positive side, because 2 to any power has to be a positive. Then when you come down to the next one, if you're doing the inverse, so log base 2, because that's the inverse where they've traded places. If your x and y trade places and you solve it. So when you do that, what does that mean? So that means we're on the positive side of x, but down really far negative on the y. Remember when you do an inverse, your x and y swap, and yet when you switched your 0, 1 to 1, 0, and you could plug those in and see that's how it works. And then how this goes up along the y-axis, this can come out here along the x-axis. And the other thing is, do you remember on inverse functions, there's supposed to be reflections over that y equals x line. So that would be the other way to look at that problem. So this, let me highlight this over here. This yellow graph that I highlighted in blue, that would be my y equals log base 2 of x. Well, what do you do in a problem like this right here, where they want you to now do the log base 2 of x plus 3? You could plug all the points in to see. I think by now we've done enough transformations that you should remember that a plus 3 on the x, that takes my basic log base 2 of x graph, the highlighted blue one over there, and moves it 3 to the left. So if we take this 1, 2, 3, 1 left of that is my vertical asymptote. And then it's going to be scooting up from there up to the right, kind of doing exactly what that blue highlighted one did. All right, so continuing with that. So if y equals 10 to the x plus 1, and we're supposed to find the inverse, remember that's where you flip your x and y around. And now you try to solve for the y here. So remember when your exponent has the y in it, we have to do a log. So this is log base 10, don't have to write it if it's base 10, of the x equals this y plus 1. And then when you subtract the 1, it's either going to be like this, or we've looked at in class before too, where that minus 1 might be written out in front. And in this case, that might be a better way to write it so that minus 1 doesn't sneak inside of here with the x. So your inverse function there would be this, one of those two forms. What about if we have log base 7 of x plus 5 and we want the inverse of that? Well, remember when you're doing that again, this is like y equals, and you switch your x and your y around. And now you got to solve for y. And remember your variable, if you're trying to solve for it in here, you have to change back to an exponent problem. So it's base 7 to to the power of x equals what I'm taking the log of, my log expression there. And then after that, this plus 5 got to go over here to get y alone. So I would have 7 to the x minus 5 like that, or if you want negative 5 plus 7 to the x. And that whole thing is going to be this inverse function of g. So one of those forms. Okay, so inverse of a log is a exponential, and an inverse of an exponential is a log. All right, so then they come to this one where they tell us that the revenue, the sales revenue, can be calculated by taking 12 times the log of A, and A is the advertising we do. And so remember, a log, the whole log graph looks something like that. You know, it goes over there, the inverse of the exponential, so the reflections over that, y equals x line. And see, if it kind of makes sense. You know, at first when you spend some money, you get some bang for your buck, but at some point out here, you're spending money and it's not increasing near as much. So find the inverse of this would be, again, where you're switching the A and the revenue variables around. And now you're supposed to solve for this R. So remember, you got to get your log alone first before you change it to an exponent. So first I would subtract the 5 to get rid of that. After I do that, I would divide by this 12 to get rid of that. And now I would be down to this point. Remember, once your variable is in the log, and that's all you have left, now you change this to an exponent problem. So my exponent problem, base 10, nothing written, you use base 10. This whole thing over here is my exponent. Gross, yes, but that's just how it works. Equals what the expression is I'm taking the log of. And so to get the R alone, subtracting that 1 over, whether you write it as the same 10 to the power of A minus 5 over 12 minus 1 like that, or in this case again, it might be better so that that minus 1 doesn't sneak up in your exponent, put it out in front. And since this R now is when we flip the variables around, this is really the inverse of this A equals that we had to start with the advertising costs. So this is the inverse of A, which a lot of times will be just written as A to the negative 1 power here instead of that R. Okay, but it is how the R formula would look if you did. All right, so how do you undo the original formula? Again, is what we're talking about. Or wait, which way? This was the inverse of R. R was what we started with, and we flipped the variables around. So I think I just wrote that wrong down here when I was looking back. That blue, dark blue formula up there, I didn't see that. So we flipped them around. So this is the inverse of my original R formula. All right, we got 2 planes. One of them's taking off, and then the other one's taking off. So when they, you know, initially when they take off, and then they reach the cruising altitude, so it levels off. So you've got this sort of a shape. That's again my log, sort of a shape there. So if you come back and then they gave you this one with 2 points. Over here they gave you a formula for calculating the altitude, and they're asking which one of them between 10 and 15, I think these were minutes, yeah, between 10 and 15 minutes, which one had a greater rate of change or which one was steeper. So we need to find the altitude of these 2 points here. So put in the 10 and work that out. Put in the 15, this 15. In for that time and work that out. Whoops, I don't want that 15 right here. I was like, it's gonna Say that's confusing. Why didn't they use two different numbers? I wrote the wrong thing. That's the 1,000 here. And then we're going to just do like the slope. So how much did it change between these 5 seconds versus how much does it change between these two fives? And that'll give us our greater rate of change. So crack-a-lack that out on a calculator. And I've got my 90, 200, natural log, ln of 10, enter, plus my 1,000, and I came up with 22,183.8, rounded off. And then the second one, the 9,200 ln of 15, enter, and add on my 1,000, and get a 25,914.06 or 0.1. Subtract those two, 25.91 times my 22. And come up with a difference of like 3730.3 versus over here, subtracting these two, my 39,440, oh wait, 39,449 minus my 37,497 and got 1,952. So it really isn't even close. This one has a way greater rate of change unless I made a mistake in my calculations somewhere. That's it for that 6.4 lesson overview.